Right. So we have been looking at a few interesting gates, right? But simple gates. But hopefully some of these concepts, right, are already forming some intuitions, right? Basically, we have this complementary network, right? We have a PMOS network and NMOS network, right? Any one of them will be on, and only one of them will be on at any given time. We usually call the PMOS network as pull-up network because it's pulling up the output level. Okay, it's connecting to the VDD, right? High voltage, pulling up. And we call the NMOS network as pull-down network. It's pulling down the voltage. Okay, it's hopefully intuitive enough. Right? And later on, make sure you check, right? So when I ask you guys to draw this kind of CMOS right network, make sure you guys check, right? So you have the same number of NMOS and PMOS transistors. They always come in pairs. So that's why we call them complementary. And you probably can already tell, right? Some of the interesting patterns here. So by looking at this example, this is the shape of this PMOS, the PMOS network and NMOS network. They are also sort of dual to each other, right? They're complementary. If you look at this one, we have parallel structure, right? Q2, Q4, they're in parallel, and the corresponding transistors over here, they are actually connecting to the same inputs, right? We have a 3 input gate here, right? Using CMOS transistors. So Q1, Q3, Q2, Q4, they are connected to both A and B, right? So if you have parallel structure in the pull-up network, in the PMOS network, we have a series structure in the NMOS network, right? Vice versa. This is this is another way to appreciate this why this is called CMOS, right? Complementary. And right, again, pull up, pull down. Okay. Right. And actually, when we look at this, right, I already mentioned, we will actually just need to later on maybe analyze the CMOS. So you guys don't have to expand the truth table. You don't have to look at each individual switch. So just focus on these structures, the substructures or subnets. Okay, it's a sub network, right? So that's why I call it subnet. Just focus on what kind of structures do we have? Do we have a parallel subnet or a series subnet? Okay, once you understand this, so things will be fairly straightforward. And actually, this kind of a structure can be hierarchical. Okay, we'll see what that means. All right, so first, let's take a closer look, right, at some of these definitions. So by series subnet, okay, regardless whether it's an N-type, right, NMOS or PMOS network, when it's combined in series, right? So to make a connection, to make sure this thing conduct, right, to have a flow, all inputs, right? So must make the connections, right? All inputs, basically all switches on this series path must be on, okay, to have a connection, right? To have a connection. Make sense? Okay, for series, and for parallel, and one of this, right? At least one of this, transistors or switches needs to be on to make a connection, right? So hopefully you guys, sort of see the analogy here. For series connection, what kind of a Boolean function does it correspond to? Very good. This is sort of like AND, right? Okay. And parallel, how about parallel? Or, okay. So we get this intuition, then you can easily translate CMOS network into Boolean functions and vice versa. Okay, we'll see how this is done. Okay, all right. So first, again, let's look at some concrete examples. Okay, a 2-input function, A and B, right? The output is F. Output is over here. So this is not a complete. Okay, first, this is not a complete network yet. This is just a subnet. Okay, this is just a subnet. Right? This is a series subnet. Right? This is an N-type series subnet. So because all the transistors are NMOS transistors, and this is pulling down. Right? If this is, we have a connection, If it conducts, then it's pulling down. All right. For this kind of structure, F is 0. F is 0. F pulls down to 0. Then both A and B are high, right? Or both A and B are 1. Make sense? Right? Okay, this is a series connection. And this basically translates to a Boolean expression like this. Right, we just talk about basically series subnet, right, correspond to AND, right? This AND, right? This kind of conjunction form, right? AND. And the Boolean expression, right? This subnet correspond to this Boolean function, right? When both A and B are 1s, we get a 0. Then both A and B are high, we get a low on the opposite side. Correct, right? Okay, this is hopefully intuitive enough, right? And again, this principle of duality kicks in, right? So once we have this kind of right, series subnet for NMOS network, we can directly draw the corresponding PMOS subnet using a parallel structure. Okay. So these two are equivalent in terms of their functionality. Okay, let's just see, right? This is in parallel, right? Okay, so this means that actually this is usually connecting to, let's say this is connecting to VDD, right? Let's say the subnet. This is also not a complete network yet. The subnet, this is in parallel. So this means that when A or B, right? If either A or B is 0, right? It's conducting, right? We have a connection, right? A or B. Okay. But we need either A or B to be 0. So that basically translates to this expression. Okay. If A is low or B is low, F is 1. F is high. And according to De Morgan, so it's the same with this, right? Which is something that we just saw. Right? Okay. These two are the same. Okay. So when you have NMOS, you can draw a corresponding PMOS network. If you can also do, if you're more comfortable with PMOS network, if it's in parallel, then you can draw the corresponding NMOS network in series. All right, so just want to further convince you, right? This is true, right? We can also have NMOS subnet, right, in parallel. In this case, right, we have a connection, or this whole network is on or conducting when either A or B, right, is high. This one, right, over here, this one. This translates to this Boolean expression, right? Because if either A or B is high, we have a pull down, right? F is pulled down to 0. Okay. Right. So this is the expression. And correspondingly, so this is the equivalent, right? This is equivalent. Yeah, this is equivalent to the NMOS, the PMOS network, right? In series. Right. Over here is basically saying that right, if when A is in series, when A and B are both low, we have a connection. Right? F is 1. So right, when A and B are both lows, we have 1, which is the same with this, according to De Morgan. Again, same thing. All right. Okay. All I want to convince you guys is, when later on you draw your network, okay, you only need to focus on one part, either NMOS or PMOS, and you can derive the other one, okay, by just doing this, right? So this kind of a changing the dual form, right? So by changing parallel structure to series and vice versa. And the reason we need both of this is, again, the NMOS network. So it's only one of the network can pass equal 0, and the other one can pass equal 1, right? So that's why we need both of them in this CMOS transistor. Okay. All right. So we just talked about how do we, right? So over here, hopefully later on, when I give you a subnet like this, you can quickly figure out the boolean instruction, right? So you can go from the network, right? CMOS network, either NMOS or PMOS, can tell me the boolean instruction. Okay, and may also give you a question like this, right? So if I showed you a CMOS network like this, can you provide the corresponding boolean expression? Okay, so there are two ways. Okay, the brute force way, right, where we enumerate all the input combinations, or we just inspect. Okay, I prefer that we do this. Okay, so I prefer that we just look at the structure of the network instead of expanding the truth table, right? Right. So this is the harder way, right? This is the brute force way. We can always do this, okay, which is less productive, especially when we have more inputs, right? The truth table is going to grow exponentially. Instead, I would rather just make sure that you guys just look at the network and tell me what exactly is the boolean expression. So let's take a stab at this. Right. So maybe let's just focus on the how about the NMOS network first, right? Because we are not inverting, right? So we don't have active low. To some of you, this might be more intuitive, right? NMOS network. What is the corresponding boolean expression for the NMOS network? Oh, actually, the moment you figure out the boolean expression for the NMOS network, you're done, right? The PMOS network is doing the same thing. So let's just focus on the NMOS network. So let's look at maybe, again, just decompose it, right? So this is not quite purely series, also not quite purely parallel, right? So let's look at the series part. This is a series subnet, right? Right? Okay, so what's the corresponding expression for this? For this one to be making a connection. AB, right? This one to make a connection, we just need AB. Let's worry about Z later. Okay. We need both A and B to be high, right? To make a connection. How about this one? This path, there's a single transistor, right? So it's in parallel. There's a Q5 is in parallel to the series structure that we are circling, right? So basically for the NMOS network to make a connection, what is the boolean expression? A and B plus C, right? Clear? Okay, very good. So you guys are getting this, right? Are we done? Is this the boolean expression? Yes or no? No. Okay. All right. What's missing? Very good. We have to negate it. This is an NMOS network. We are pulling down. Okay, we're pulling down. Okay, we need to negate it. That's it. All right. Okay. We can also take a quick look at the PMOS network, maybe, right? Just to convince you guys, this is the same thing, right? So for the PMOS network, let's look at the parallel structure first, right? There's a parallel subnet. What is the corresponding boolean instruction to make the connection, to make it conduct? A naught plus B naught, right? Make sense, right? We need either Q2 or Q4 to be on. All right, how about Q6? Q6 is connected in series, right, to this parallel structure. How do we combine Q6? We just need to end C naught, right? And this is the same thing, right? So the PMOS network is the same. If you do De Morgan, this is basically right. These two are the same. Okay, that's how we analyze, right? And we just talk about, right, these two expressions. Any questions? If not, Okay, so let me just quickly, we don't have to, you guys don't have to read through the whole thing, right? So this is basically what we already said, right? Okay, and this is just, we just try to make it, work the other way, right? So if I give you guys a Boolean expression, how do you construct a CMOS gate? How do you construct CMOS network? Right? So all you need to do is just focus on one of them, right? Let's say this is the, right? So this is my function, okay? And see here, it's already negated, right? At the end, all you need to do is, right, just look at this function and see if you have a OR, right? So like this, you have a parallel structure, right? If you end over here, you do it in series, right? That's how you construct it. And this is how you construct the NMOS network, right? That's it. And then you just have to sort of convert it, right? So you convert parallel to series, then convert series to parallel to the corresponding PMOS network. And then you concatenate these two together. That's it, right? So that's how you construct CMOS from Boolean instructions. Okay. All right. I think we have 1 more minute, right? So let me just show you one more slide. Okay, actually maybe two more. This is just a sanity check, right? That we have to do. So later on when you construct network, just check, right? So we do have the equal number of NMOS and PMOS transistors. And the NMOS network is tied to the ground, PMOS tied to the VDD. Okay. And we have the equal number of them, right? And they're all tied to both pairs, right? All the pairs, right? Check all the pairs. Each pair is tied to the same input. This is a sanity check. All right. Okay, so one last exercise before we go. Okay, this is just to convince you guys, this is a NAND gate is indeed interesting. What is this? Any guess? What is this? First, what is on the right-hand side of the red line? What is that? This one. What is this? It's a NOT gate, right? We just saw that this is an inverter, it's not. What is on the left-hand side? Something that we just learned, right? The left-hand side is a NAND. Okay. What is this whole thing? It seems sort of convoluted, right? What is this whole thing? Okay, this whole thing is basically AND gate. Okay, this is just AND gate. All right. Okay. Right. So this hopefully this is interesting to you, right? So actually, you want to implement AND gate using CMOS, we actually have to do this. So this is actually more expensive than NAND. Okay. So we need 6 transistors. For NAND, we only need 4 transistors. That's why we like NAND, right? When we use CMOS as the underlying technology. Right. Of course, in many cases, we will just use AND and OR, right, in an abstract way, right? If you don't think too much about CMOS. All right. Okay. This is the final slide for this lecture. Okay. I think we are done. Okay. I'll see you guys next week. Thanks, guys.